Hello, morning everyone.
Good morning.
Can you hear me?
Yeah, I can hear you.
Okay, great. Thank you. Okay, think let's start. Let me try to share my screen. Okay. Okay, so you should be able to see my screen. Um, yeah, I think last week we finished the sub chapter of the IP protocol, right? We talk about something related to IP datagram format, addressing, and the network address translation, and we also mentioned something about IPv4 and IPv6, right? How to make the different versions of IPs compatible with different router devices, right? So if some devices are not upgraded to IPv4, so how we deal with that? Uh, so that's something we have discussed. I think today I want to finish this chapter. Okay, we will generally discuss about something related to generalized forwarding. Usually will be used in the software-defined network, and we will mention something for the middle boxes and to close this chapter. Okay, let me know if you have any question during the class. So I think let's talk about something about the generalized forwarding, match plus action policy. Okay, so let's first try to review if a router contains a forwarding table, right? So you know that we have the forwarding and the routing algorithm. So routing algorithm is more global view, right? So of that, each router should have the forwarding table. As still, I think you still remember that, right? So so far we don't cover the routing algorithm. So in the old textbook, usually this chapter would consist of several famous, for example, Dijkstra algorithm, some graph algorithm for the routing classic algorithm. Okay, but so far I think for the new textbook, this is not the emphasized check section because it's a too algorithm oriented. Okay, but in your mind, you may think about some control flow, some optimization graph problem, right, for the routing. Okay, but that's from the large global view of the different routers, different hosts. Okay, but for the local view that each router contains a forwarding table. Okay, and we introduce a concept of abstraction is a match plus action. So match means that you match bits in arriving packet and take action. Okay, this like how you proceed with the forwarding action. Okay, so you get some packet and then match the bits in the arriving packets and take some action. We will introduce what kind of the bits you want to match and what kind of the action you want to take. Okay, so generally speaking, in general, we have first we have the destination-based forwarding. It's just based on the destination IP address and try to forward that datagram to some output link, right? So I think you let me change my laser point. Okay, so for example here, right? So you still remember previously we matched the IP address and for example 011, right? We try to based on the forwarding table, we try to forward it to the output link two right here. So this is just a destination-based forwarding, right? So we have some more generalized forwarding idea. So For example, so many headers fields can determine the action, and the many actions possible could be drop, copy, modify, log packet. So I will give you an example here later, but I mean, so here is a general speaking, we have two kinds of the forwarding. Is first is based on the destination, right? Another is a general forwarding. We can drop, we can block, we can modify the packet. Okay, so that's the I will talk about that later. But I mean, the general idea is that we want to have some software defined networking action, right? So if you can add some software component to the current network previously, because as I mentioned, you um, almost the hardware component will determine how you forward the packet, right? How you make forwarding based on the router hardware itself. But now, as I show in a previous video, right? So you have some software defined network. You have some software component can be integrated into your network, can help you to manage the network more efficiently or more smartly, right? So we need to have some design here. So first, let's see the flow table abstraction. So the flow defined by header field value. So for example, here is the in link, out link, network, transport layer fields. So there is something related to the header fields value. Okay, and we have some actions here. So first, as I mentioned, so we the abstraction is a match and action, right? So match is pattern values in the packet header fields. You just try to look into the packet header fields and then take action. So for the action, it could be a drop, forward, modify, match packet, or send matched packet to some controller. Okay, so we will cover each one in the in a animation, okay, or in an example. So also we have the different priority for the flow table abstraction. So the flow table abstraction can give some priority here, which packet after you match, right? After you take action, which one is the priority and how many counters for the bytes and packets. Okay, so this is some information be shown in the flow table here. So for example, here is a quick example. So in the flow table, we can see here, if you want to match, star means the wild card, right? So if we want to match destination 3.4 dot something, and then forward 2, what does this mean? So this means that if you find some packet, the destination is started with the destination IP started with a 3.4 dot something, right? You just forward this packet to output link 2, right? So this is the first entry, or maybe not first entry, but one of the entries in the table. Okay, and also you can have something like, for example, here, if the source destination is 1.2 dot something, and no matter what kind of destination it is, it just drops this packet. Anyone can think about why we want to define this match and action in the flow table. If you find some, for example, packet from the source 1.2 dot something, you just drop it. So what kind, why we want to have this function?
Maybe that packet is being broadcast to multiple routers and it doesn't need to be forwarded from this one.
Yeah, this could be, yes, thanks. This could be one of the possibilities, right? Another possibility could be if you want to define firewall, right? If you want to increase the security of the network, if you identify that some IP address in, for example, 1.2 something, and it's a bad IP address, or you detect some bad actions before, right? You put this in the blacklist. Then if you find that this flow table could help you to automatically drop the packet. It means that you cannot access the network, right? So yes, that's a different I mean possible reasons, right? So you can help the network to have a better management here. And also you can see here, if I have the source IP of 10.1.2.3, I just send it to the controller, right, to do some following actions, right, like encapsulation, right. So here is something we can see in the uh, flow table here, right? So match and action, match and action. Okay, this table shows this kind of information. And to be specifically here, okay, so we can see here, this is a very traditional or classic different layer, right? From the transport layer to the IP layer, and then to the data link to the physical layer, right? So we can see the flow, OpenFlow is a framework, right? To have the, I think OpenFlow is a software defined network protocol across different vendors, different companies, right? They can kind of use the same standard protocol to define how to control the flow, right? How to do the flow, how to do the forward, how to do the drop, right? Everything in the software layer. Oops, it was stuck. Okay, so you can see here, so the match and with the action. So the action could be forward a packet to some port and drop some packet and modify fields in the headers, and you can encapsulate and forward to the controller, right? But the match condition depends on your demand, right? What kind of the demand you want to do? It's a firewall, or it's just a better routing, right? Or something, right? You can define your scheme, your protocol, your mechanism here. Okay, and then the status here is just the packet and the byte number or counters for the for different situations. Okay, so for example here, let's see some examples for the OpenFlow. Yeah, here I don't expect you to know very deeply about the OpenFlow, because this is a very complicated framework, and many networking research and the industry people are using that. But from the high level, we want to understand how maybe this framework can provide you what kind of the capability, right, or functionality here. For example, this is kind of the general API, right? Or I mean the standard API here. So you give different information, right, in this different entries of the, for example, this is rows, right? And if you put only put the IP address and action as a port 6, what does this mean? This means that if IP datagrams designated to the IP address of something you written here, right? You wrote here should be forwarded to the router output port 6. Okay, so this is the most yeah, this is the easiest or most straightforward forwarding based on only based on destination IP address forwarding. Okay, something else, because we mentioned that besides the destination based forwarding, we can also have some other um, generalized forwarding techniques here, right? So for example, as I mentioned, it could be for the security purpose for the firewall. So you put the TCP port number 22 action drop. So means that you block, do not forward all datagrams destined to the TCP port 22 SH port number, right? So if you know something about SH um, mechanism, right? You try to SH to some server. If you put the firewall here, means that the TCP port is closed. Everything trying to SH to the server will be blocked, right? So sometimes I remember previously when we configure a cluster, for some nodes, definitely we don't want to have people to SH to that nodes, right? So you can close that, but for the login node, definitely you can open that, right? So this kind of like a firewall, right? You can define, right? If you want to access to the port, you just drop the datagrams here, right? This is for firewall. Similarly, you can do as we mentioned that, right? So you block, do not forward all datagrams sent by some host IP address, right? It could be the scram or could be some something you want to block. Okay. And also there is another destination-based forwarding based on the layer 2 data link layer. So this is something we will introduce next chapter, okay? For example, based on the MAC destination. So layer 2 frameworks with the destination MAC address, something here should be forwarded to output port 3, right? So this is based on the lower layer, right? Previously we based on the IP, right? So this is based on the MAC address. So you can see that this OpenFlow framework can give you some flexibility, right? To control things from the software layer, right? You can program here, right? You can see here, right? So you just add something to the software layer component, and then you can control how to make the packet, how to make the datagrams blocked or forwarded, or what kind of the forwarding you want to expect, right? And right, so that's I think that's very general description. Okay, a lot of details here, but we just want to understand from the high level how OpenFlow will work. In summary, so here, so for example, if you have router, so match is that you want to match the longest destination IP prefix, as we mentioned before, right? You match the longest destination IP address prefix, and you forward it into the output link. Okay, switch. So, but the switch concept we haven't introduced yet, but we will introduce in the next chapter. So you similar as you see in the example, you have the destination MAC address, you just forward or flood, right? Flood is some concept we will discuss next chapter. Okay, but just the different schemes based on the different MAC addresses. Okay, you can also have some forwarding and flooding here. And firewall, as I mentioned, so that you can match the IP address or TCP, UDP port numbers, and you can decide to permit or decline or deline, right? You give the permission to access or just drop that. And similarly, you still remember for the network address translation, right? So you can translate the IP address and the port number to the outside of the word, rewrite address and port. Okay, so this is like open flow abstraction, defines the different kinds of the device and different functionality here, right? So for router, for firewall, for NAT, for switch, right? You can all define them in a software layer. Okay, that's why we call it software defined network. You can program something here. Okay, let's continue to see example. Um, so for example, if you have the OpenFlow controller, like you have some centralized control here, right? As I mentioned before, if you want to have the network to be smarter or to be more efficient, you can have some better design for the network flow, for the forwarding, for the routing, right? So if we require, for example, you do some investigation, right? And you find, okay, let's make a datagram from host H5. So this is the host H5, right? And the host H6. So these two hosts should be sent to H3 and the H4. So where is H3? Here is H3, right? And where is H4? This is H4. Okay. So we want to make, we want to make this is oops, why I cannot use a pen here. Okay, we want to make this one and this one, right? To send the datagrams to 3 and 4 here, okay? To do what? To go through S1 and then S2. Where is S1? Here is S1. So we want to go this way, right? To here, from here to here, right? Sorry, I should plot in this way. Okay. So for example, from H5 to H3, I should go from the 3, 1, 4, actually from 3 to 1, 4 to 2, and to 3, right? Anyway, I mean, so for this pass, right? So I hope I didn't plot very confused. Okay, and similarly from S3 to from H6 to H4, right? From you should go from this way, right? So this is our assumption, right? We want to have the network to go from this specific path, not maybe go this way, right? We don't want to go this way, okay? So how should we do? In the OpenFlow example, we should have designed some, as I mentioned, we should put something in that in this format, right? So in this format, right? We want to design something like this, right? To make the network forwarding to follow our design idea. So how should we add this part? Okay, so maybe I should, can I, can I clean that? Okay, okay. So yeah, this is exactly what I plot, right? And how should we put into the open flow entry? How should we add this component? So for example, from the, let's say from H5, right? This is a H5 destination is a 10.3.0.5, and H6 is a 10.3.0.6, okay? Other than these two IP address, all of the other IP address is a 10.1, 10.2. So let's say for the IP source IP, let's say 10.3 dot something, right? If the message or packet starting from 10.3 dot something, that means from these two hosts, right? And we forward that to 3, okay? So then based on this action, we can limit all the packets starting or sent by the H5 and H4 to go this way, right? To go this way instead of this way, okay? Because based on our assumption, right, we want to go through S1 and S2. We don't want to go to the uh, this way, right? We don't want to go to this way, right? Okay. And this is the first forward. So after this forward, we should define next forward. Is that right? Because after that, it only access to this router, S1 router. We have to make sure it will not go to the other way. We have to make sure it will go from to this way. Okay, so we should have another forward. So here, so if the incoming address port number is 1, right? Because we coming from 1, and you should forward to 4, right? And the source IP address is for the 10.3 and 10.3 something. And the destination is for these two, right? 10.2 something. Okay, so this is the second forward we define in the network. And the last one is that after we go to the S2 router, we just add something to separate the traffic to 3 and 4, right? So for example, if both are coming from 2, but if you want to go to the destination 10.2.0.3, you should forward to 3, right? If you want to go to 10.2.0.4, you just forward to 4. Okay. So then you finish this what you want to, I mean, this is kind of like implementation detail, right? This is a high level description. This is a high level description, right? You want to have some datagram from H5, H6 to be sent to the H4, and H3 goes through S1 and S2, right? Just one sentence, but you need to have some defined forwarding scheme here. If you want to implement in the software, it should be implemented like this way. Okay. Any question for this part? I think this is a kind of straightforward, but maybe I just want to um, emphasize that here you need to have the two forward because eventually you need to go to the destination of 3 and 4, right? So you will have two different forward here, okay? So if no question, let's try to summarize here. So here is the generalized forwarding, right? Not only based on the destination IP address, you also want to do something based on what you desire to do, right? You want to have some controllability, you want to have some security level, right? So the match plus action abstraction, so means that you match based in arriving packet headers in any layers, right? In any layers, not only in transport layer or the data link layer, right? You can do for the different layers and you can take action to matching over many fields, right? Link, network, transport layer, different layer here, right? You can do some local action, so you can drop, you can forward, and you can um, do the drop forward, modify, and send match the packet to the controller, right? To the different controllers. So the program network-wide behavior. Okay, so it gives you some programmability. So I think some of you may know that, but I assume most of you may not know that network programmability is a very hot and important topics in today's networking system. So not sure if you know the company about the company Mellanox, right? Mellanox just was acquired by the NVIDIA, right? So that company has a many very high speed networking product for InfiniBand networking switch, right? So I think one of the reasons NVIDIA purchased that company is um, Mellanox has a very good technology for the networking programming. Okay, they are trying to program the networking. For example, here our example is a very simple. I mean, it's a very simple example, but can demonstrate some idea. If you want to program the network, right? You want to specifically, for example, match some packet to make it forward or routing algorithm specifically, right? So what you can do, right? You can make your network component to have some programmability, right? You can program the network, and the network can follow what you want to do to deal with the data packets, right, or datagrams. So the idea for this is that you can offload some computation to the network itself, right? You don't need to take care of everything in the CPU or in the processor unit, right? You can offload some, for example, a dynamic thing. You don't know how your traffic would be during the runtime or during the real uh, scenario, right? Then you just offload some computation to the network. The network based on your program, right? You program something in the network, and based on your program to configure the traffic, to forward the traffic, to route the traffic, right? So that would give you some good capability here. So as I summarize here, so the simple form of network programmability, it can be programmable per packet processing. And for today, some more generalized programming like P4, it can even do some compression to do some more complicated thing in the network, okay? Uh, but as I mentioned, that's something you do in the software defined network, right? It's not hardware component. It's not initially be designed in the hardware, right? You do something in the program, in the software, okay? So that's the idea for this sub-chapter. Any question before I finish this last sub-chapter to close this section? Okay. Okay. So if no question, let me continue. So nothing about the middle boxes. This is more like a, concept things. So what is the middle boxes? So the boxes, based on the definition, is that any intermediary box performing functions apart from normal standard function of an IP router on a data path between the source host and the destination host. Okay, it's like something no, different from IP function. Okay, all the other things called middle boxes. So why we need to know some middle boxes, and I think middle boxes are everywhere. So for example, what is the IP function, right? IP function is just it's just based on the IP address, right, to quickly identify the destination. Other than that, other functions are middle boxes. For example, NAT, translation, network address translation, right? Firewall or some IDS and load balances and application specific some functions. All the other functions are the middle boxes. Okay. Why we are trying to talk about this? Because also caches. Okay, why we talk about this? Because I think uh, the initially, right, the function, I mean, as I mentioned, are all based on the hardware solution, right? Now we are trying to move towards white box hardware implementation open API, right? We move away from a hardware solution. We just try to add something into the network, uh, but based on the programmable local actions, right? Through the match and action, and we want to move towards to the software defined network. Okay, so this is what we have already mentioned, I think. And I think this is a feature I recommend you to think about it. That so you can see here for this picture, different. This is a traditional layers diagram, right? So this is the application layer, right? So this is the transport layer. This is a network layer, right? And this is a link layer. This is a physical layer, right? So we can see here, all the different layers have different kind of protocols, TCP, UDP, HTTP, different things. But here we can see no matter what the protocols you use, above or lower, IP address is the only thing you must go through. Okay, so you can see when data transmission through the four layers, the 1, 2, 4, 5, right? These four layers is visualized. It takes you can see the shape of the hourglass as this one, right? So this is a thin waste part of this diagram, and all the datagrams has to be passed through this layer. Okay, so no matter what you define the other protocol, other layers, this IP layers is something you must go through. Okay, so they must be implemented by every billions of internet connected devices. So why this we call it IP hourglass, right? So you can see many protocols in physical link transportation and application layers, but this is something we definitely want to do. And okay, so after you have this software defined functions, right? It can help you to expand the IP functionalities, right? So middle boxes can operate inside the network. Okay, it can help you to expand this layer a little bit and give you more capability or functionality here. Okay, so this is something we call it middle boxes. And okay, here is another principle called the architectural principle of the internet. I just want to quickly go through that. I think this is a straightforward, a simple connectivity IP protocol that narrows waste and intelligence complexity as the network edge. Okay, so this is some like architectural principle. So I will explain later why here we introduce several principles and several new concepts here. Okay, otherwise maybe you will be confused. So just just see here, here, this is called the architectural principle. Okay, the goal is connectivity, the tool is the internet protocol, and intelligence is end-to-end rather than hidden in the network. So this is the architectural principle of the internet. And here's another some argument for some network functionality like a data reliable data transfer congestion can be implemented in network or at a network edge. So what does this mean? This means that some functionality can be implemented uh, in the end-to-end or in the network. Okay, it has different implementation strategies. Okay, to realize some functionality. For example, as we mentioned, we can use a TCP UDP, a TCP protocol to guarantee the reliable data transfer. Or we can make sure that we can make it that through the network itself, right? We have the different strategy to guarantee this reliable data transfer. Okay, but the end-to-end argument is we I think the key point is that we want to make this feature to be transparent to the network level. Okay, we want to make the feature to be only visible to the end-to-end points level. So here is a more detailed definition. Okay, so the function in question, so here is some network functionality like a reliable data transfer can be implemented in network or at network edge, right? And the function in question can completely and correctly be implemented only with the knowledge that and the help of the application standing at the endpoint of the communication system. Therefore, providing that question the function as a feature of the communication system itself is not possible. Okay, we call this line of the reasoning against the lower level function implementation the end-to-end argument. I mean, this is a kind of a long description or whatever is a complicated thing, but if you want to summarize or what is the conclusion based on this argument is that according to this principle, the application specific feature like a reliable data transfer, right? You want to have a reliable data transfer. This is the application specific features resides in the communicating the end nodes of the network rather than the intermediary nodes, such as gateway or routers that exist to establish the network. I mean, the one sentence is that the application features resides in the end-to-end end nodes instead of the uh, intermediary nodes, such as the network gateways or routers, right? You just keep your application features visible to the end-to-end nodes here. Okay, so why we need to do that? What's the benefit to do that? Okay, I mean, I can use an example to quickly explain the idea, because where is the intelligence in maybe 30 years ago, right? So in the 20th century phone net, what you can do is just you can put the digits in the endpoint, right? The other things need to be take care of, intelligence need to be take care of in the network, right? So you cannot do many things in the endpoint, right? You just dial in and someone just reply with some digits. You can answer the phone, whatever. You cannot do much intelligent things here, right? For the network traffic, for a lot of things, it has to be here, okay? You can think about the brain. So the intelligence is happening here. So this is something for the many years ago, 30 or 40 years ago, right? So for the phone net, right? But now we have some internet, right? Internet also have some different period, right? So you can see here the internet, when the internet invented, right? So you can computing something in the edge, right? So different device have different intelligence here, okay? So that's why I mean the application specific feature can be removed from the network itself, right? You don't need to have the network to deal with these complicated intelligence things. You have to do that in the endpoints, right? And just ask the network to do some very generic uh, communication and uh, transfer, right? You just give the intelligence to the endpoint here. Okay, so this is the one internet pre 2005 intelligence computing at the edge. But now, as I mentioned, you can do some more fancier things here, right? You can do some program in the network devices, right? That add more intelligence to the endpoints. Okay, and you can see we have some mailboxes as we middle boxes as I mentioned, right? You can do a lot of blocking, forwarding, a lot of things in the end, and based on the programmable network service devices, right? So you can give them more intelligence and computing power and massive application level infrastructure at the edge. Okay, so um, that's the point. Okay, when the internet come along, the endpoints and the switches were both programmable computers. You can put a lot of complexity here based on the architectural principles and the end-to-end arguments here. So that principle developed a lot of years ago, but people, wisdom people see the trend of the network, right, to give more powerful uh, capability to the end here. Okay, so I think that's why we talk about some conceptual things here to demonstrate how the future network will be developed, I guess. So in the future, SDN and the network programming would be, um, you know, very important. Yeah, based on this explanation, I think. Okay, so I think that's pretty about this chapter. Um, I think we survive for the lot of contents for this chapter. Okay, we cover, so there's some additional slides, but I don't expect you to understand detail about that. Generally speaking, it's about the IP fragmentation and reassembly. Okay, it's not complicated, but anyway, just some extra slides. If you are interested, you can take a look at it. Okay, so yeah, that's most of the chapter for the IP for the network layer. Okay, any question? I think for the last middle box, a lot of some new concepts here, but I explain that quickly because I think that's something only related to the future development trend. So the most important idea is that where is the intelligence, right? So previously it's here, but now it can be spread all of the endpoints and become more and more powerful. Okay. Any question? So I think for the assignment 3, I guess TA would post the grade this week, and I'm gonna to post another assignment for the chapter 4. Okay, and set a deadline maybe for 1.5 weeks. Okay, everything's good. Okay, if no question, let's close here today. Thanks everyone, and see you on Wednesday. Okay, see you. Are these slides posted? Okay. Uh, I thought okay, I got it. Okay, so I think I posted the video, but not the slides. I will post it right now. Okay, thank you for a reminder. Okay, have a good day. Bye bye.